I got a couple example problems I want to do with you guys or for you guys before we move on to the next little part here. The first one, and it's just using what we've learned in the first period today. Hopefully the guys got a chance to check out the video from the first period here. But we have, excuse me, it is known the Earth's magnetic field over northern Canada points straight down. The crew of a Boeing 747 aircraft flying at 260 meters per second over northern Canada finds a 0.95 volt potential difference between the wingtips. I don't know how they got a voltmeter out onto the wingtips. Maybe they're always there. I have no idea. The wingspan is 65 meters. What is the magnetic field strength there? All right, so basically we're looking to use what we know about magnetic fields to, what we know about this kind of induction of potential between the sides of a conductor when it's passing through a magnetic field to figure out what the magnetic field strength is. So maybe we look at like the top-down view of an airplane, and who knows if it's actually worth drawing this out, but right, if our airplane looks like this and it's got wings out here, right? So we're obviously one wing has to be way bigger than the other wing. That's just how airplanes work. So 65 meters all the way across. We're going to assume that the plane is made of conducting material, right? Because if it's not made of conducting material, it's not going to work. And it's in a magnetic field that points straight downward. So if we're going for a top view, excuse me, then the magnetic field would be straight downward. That would be X's. All right, so here's our magnetic field. Our velocity, hopefully, if airplanes work the way I think they do, our velocity is in the direction of the front of the airplane. So we have velocity, we have magnetic field. If we look at it the way I have it drawn, velocity is up the page, magnetic field is into the page. That leaves my thumb pointing to the left. So the force on the charges, if we put a positive charge on the plane here, it would feel a force this way. So we get an accumulation of positive charge on the left wing, an accumulation of negative charge on the right wing. We know what that potential difference is, right? They gave us that the potential difference between these wings is going to be 0.95 volts. So can we take that information and figure out what B is equal to, right? That's the goal. So based on what we learned today, we actually have an equation, pretty easy equation that's going to help us out with this, right? Delta V is equal to velocity times the length of our conductor times the magnetic field. And we have potential, we have velocity, we have length. We're solving for V, or solving for B. So this is pretty much like a one-step equation, right? We have everything we need. We don't need to do anything crazy. So 0.95 equals 260 times 65 times B. We divide over 0.95 divided by 260 times 65 will give us B. And if we do some quick math there, B ends up being just about 5.6 times 10 to the negative fifth Tesla over northern Canada. If you guys look back in the book, there's a table that gives the average magnetic field strength of the Earth at about 5 times 10 to the negative fifth Tesla. So magnetic field strength near the poles, right, up near northern Canada is a little bit stronger. Magnetic field strength towards the equator is a little bit weaker, balances out to around 5 times 10 to the negative fifth Tesla. All right, nice, easy one to start. Question number 2, or example number 2. A metal bar of length L rotates with angular velocity omega about a pivot at one end of the bar. Uniform magnetic field B is perpendicular to the plane of rotation. What is the potential difference between the ends of the bar? So I'm going to draw this so that it's easy for me. Actually, let me do it in black. I've been doing magnetic field in blue. I should be consistent. So we've got a bar rotating from a pivot point. I guess it doesn't matter which way we make it rotate, right? It doesn't specify in the problem. So maybe we make it rotate down. All right, let's say it's rotating clockwise. So omega is clockwise. And we'll put the magnetic field into the page. So it's in a magnetic field that is into the page, right? So there's our magnetic field. We're rotating around counterclockwise. Maybe I put some whoosh lines here, right? To let us know that it's spinning around. Right? That's how we show motion in physics class. Spinning around. Okay, so let's look at just a single particle to start with, right? If we have a positive particle inside our conductor here, what direction does it feel a force if it's in this magnetic field? So this one's going to be a little bit hard for me, but velocity is down, magnetic field is in towards the page. That leaves my thumb pointing to the right. So my particle, my positive particle, is going to feel a force to the right here, which means I'm going to end up with an accumulation of positive charge on the rotating end and accumulation of negative charge on the non-rotating end. Does that work the same way if you use a negative charge? What if we put a negative charge in here? Does the accumulation stay the same if we look at negative charges moving? Negative charge still moving, right? Because the velocity, I guess I should specify this was force, right? The velocity of this particle is this way, right? Because it's rotating, which means the velocity of the negative particle would also be the same way. So if we have velocity the same, magnetic field the same, it just feels a force in the opposite direction. And yes, it would move that way. So the accumulation stays the same, whether we're talking about positive particles or negative particles. So we don't have to worry about that. Remember, the Hall effect was a little bit different if we were talking about the movement of positive particles or negative particles. So in this case, the particle that we're talking about doesn't matter. We get the same resulting accumulation either way. Okay. What is the potential difference between the ends of the bar, right? So we know that we're going to establish a positive end on the right side here and negative on the left. That will give us a potential difference between the two ends, delta V. What is the value of that delta V, right? That's what we want to know. So I think the best way to look at this is in terms of delta V being equal to the negative integral of E dot ds. All right, so let's start there in this case. All right, so where should we start? Let's look at the way that the electric field is established first, right? So the electric field is going to be established from right to left. I know I'm drawing a lot of stuff on this same little image here, so I'm sorry if it's a little bit confusing, but electric field always goes from positive to negative. So we get an electric field that's established from right to left. We saw earlier that if we went ahead and set electric force equal to magnetic force, which we're going to get if this situation has reached equilibrium, right? Electric force is Q times E. Magnetic force is Q times V times B, assuming everything is perpendicular, which in this case it is, right? Q's cancel, and electric field is equal to V times B. And in most cases, that's good enough because we're just talking about V times B. However, in this case, because we're rotating, we don't have a one specific velocity, right? If we look at the points along this rod, we have a variable linear velocity. At the very ends, we're going to have a maximum velocity, right? Where the particles are moving very fast, V, right? V is at a max. And if we look at the very base, right, at the pivot point, it's actually not moving at all. We get a velocity of 0. So we have a variable velocity here. So this doesn't help us a whole lot. We kind of want to look at this in terms of omega. So if we go all the way back to angular motion, linear velocity is equal to omega times r, right? Angular velocity times radius. So we can rewrite our electric field equation that we just figured out here as omega r times b. All right, and then we can plug that into our potential equation. So we have an electric field. We have a value for electric field that's based on the things that we were given, right? We have omega. R is going to obviously relate to L somehow, right? Because radius is the length. And we have magnetic field, which we know is uniform and perpendicular to the plane. So we have everything that we kind of need there. So our potential difference is going to equal negative omega r b dot. And because we're not talking about linear distance, right, ds, we're talking about radial distance, we'll turn that into a dr, right? It's still a dot product, which means we technically have a cosine of theta here, right? That's what, because this is E dot ds. Cosine is based on the angle between E and ds. So if we set up, right, let's say that, just to give us a value here, the pivot point is at 0 and the end point is at L. So 0 to L, R is radially outward, right? So R is going to go radially outward. We can see electric field is radially inward, which means the angle between them, right, between dr and E is 180 degrees. Cosine of 180 is -1. So I'm going to take out the dot product and replace the dot product with a negative sign because they're at 180 degrees from each other. So this is actually going to be negative omega r b dot, not dot, because we just got rid of the dot product. So omega r b dr, integral from 0 to L. Omega is constant, b is constant, so we can pull those out. Negative omega b integral 0 L negative r dr. Negative sign is just going to go away because it'll cancel with our other negative sign. So actually, I'm just going to make those positive, right? Get rid of that negative sign. Integral of r dr from 0 to L is just going to be L. So we'll get that. Actually, it's not. I lied. I don't know why I just kind of brushed that off. The integral of r is not just r. The integral of r would be 1/2 r squared, right? So we'll get omega b times 1/2 r squared from 0 to L. Just double check that really quick. Bring down the 2. Yeah, if we derive that, we would end up with just r. Okay, good. So we resolve that and we get omega b times 1/2 L squared. The 0 part would just put r at 0 and that goes away. We can rewrite this in maybe a neater form. Delta V is going to equal 1/2 omega b L squared. Boom, bam. There is our equation for the potential difference between the top of the plate and the bottom of the plate, or the right of the plate and the left of the plate, I guess, depending on how you look at it. But the potential difference for a bar that is rotating in a magnetic field with an angular velocity omega. All right, there is the second one. And the third example, we get to where we are moving our circuit in a magnetic field, which is what we kind of looked at towards the end of the class. So we have a circuit consisting of a flashlight bulb that's rated at 3 volts and 1.5 watts, and ideal wires with no resistance. So we don't have any resistance there, just besides the light bulb. The right wire of the circuit, which is 10 centimeters long, is pulled at constant speed V through a perpendicular magnetic field of strength 0.1 T. And we have 2 questions here. Let's throw some question marks on the first one. What speed must the wire have to light the bulb to full brightness? And what force is needed to keep the wire moving? So we have 2 questions there. Let's draw out our circuit first. So we have a circuit that's consisting of, I forgot to draw the bulb. I erased the entire problem. And those are just going to show back up. All right, there we go. Okay. So let's make sure we have the bulb in there. Good work, Mr. Knight. So we have a bulb. We have a conductor. Doesn't say which way the magnetic field's going, but we've been pretty consistent about saying the magnetic field is into the page. So let's make the magnetic field go into the page. And it doesn't say which direction we're pulling it, so let's pick out. All right, so we're moving our conductor to the right in a magnetic field that goes into the page. Velocity to the right, magnetic field into the page means our positive particles are going to go upwards. So if we put in positive particle, it is going to go up, which is going to create a potential difference, which will send current around our circuit through the light bulb counterclockwise. All right, so current is going up through our conductor around the circuit counterclockwise, which is going to create a magnetic force in the opposite direction. I don't know, choose this, right? So that creates a magnetic force this way. I don't know why I keep writing mag. You can just write B, right? It's a magnetic force created that way, right? Which is opposing our velocity. So we are going to have to apply a force to the right to keep it moving. We'll call that F pull, right? We're going to have to apply a force to the right to cancel out that magnetic force. So our 2 questions, right? What is this velocity in order to light up the light bulb? And then what does this force have to be to counteract the magnetic force? So those are our 2 questions here that we want to answer. So let's start with the first one, right? So to light the bulb to full brightness, we need 3.0 volts and 1.5 watts, right? So that's what we're looking for in terms of brightness. Now, that's not something that we have an equation to relate to speed, right? Right now, we don't necessarily have a conversion straight from volts or watts to speed. So I think we have to take these and turn these into a current, right? Because current, we do have a way to relate to speed, right? We looked at that equation earlier. So let's look at our power equation relating current and voltage. P equals I times capital V, right? Which is potential difference. So we have 3, we have 1.5, which will give us 1.5 equals I times 3, divide that over 0.5, right? The current through our circuit is going to be 0.5 amps. All right. That still doesn't give us everything we need, because if we look at our equation that we got for current through a circuit, the current that we're establishing in our circuit, we are looking for, sorry, I just had to check my notes to make sure I get this current equation right. My current, I draw green. So current is equal to V times L times B over R, right? So this is the equation that we're looking to kind of use to relate this stuff, right? Because it's got velocity in it right there. It's got length, which we know is 0.1. It's got B, which we know is 0.1. We just solved for I, so we have an I to put in there. The only thing we're missing is R from this equation. And we can actually use I with the potential difference using Ohm's law to solve for R there as well. So we have really everything that we need. So let's solve that really quick. V equals I times R. Again, capital V meaning potential difference. I'll just throw a delta in front of these so that we know that they're potential differences and not velocities. So we get 3 equals 0.5 times R. We divide that over, and R equals 6 ohms. So now we have R, we have I, we have L, we have B. We have enough to solve for V here. So I, we decided, was 0.5 equals V times 0.1 times 0.1 divided by 6. 6 multiplied up, divide by 0.1, divide by 0.1. We should end up with, I think, 300, right? Because that would give us 3. And then, yeah, so V is going to equal 300 meters per second. Very fast, very, very fast, right? We have to move that bar, this conducting rod that we're using, at 300 meters per second in order to get a current of 0.5 amps, which is why we talked about this in class a little bit. And if you watch the video, you'll see me talk about it, right? Converting mechanical energy to electric energy is kind of the process that we use for creating electricity, right? This process is very simplified and is not an effective way of doing that because we have to pull with such great speeds, right? How can I pull a bar at 300 meters per second, which is almost as fast as the speed of sound, right? Consistently for any kind of any amount of time, right? So just straight up pulling a wire in a magnetic field is not going to be effective for creating electric energy, right? So converting mechanical energy to electrical energy is what we're doing. And that's the process for electric energy creation. But this specific process is not necessarily effective. So the second question here is, right, we have velocity now. What force do we need to keep the wire moving? So we need to take this now and relate it to force. We have that equation as well. So let me write out this equation. The force equation is equal to, where'd it go? VL squared B squared over R, if I'm not mistaken, which I could be. There's definitely a chance that that's the case, but I think I got this one right. And this is both the magnetic force and the pulling force, right? They should be equal because we're pulling at constant speed. So we can plug in now, right? We have V, so we have 300 times 0.1 squared times 0.1 squared divided by R, which is 6. And we end up with a force of 5.0 times 10 to the -3rd newtons. So the force required to keep this rod in motion is not very big, right? The force is on the order of, what is that, millinewtons, right? Tiny amounts of newtons. but the speed that we need to generate any kind of significant current is very high, right? So we need a high speed, but it doesn't take a whole lot of force to keep the rod at that speed, which will also play a role when we kind of get into talking about the generation of electrical energy as well. But there is example number 3, solving for velocity, check, and force, check. All right, I'm going to stop this recording here and then start converting it into a file so that I can post it to Schoology.